So we have a few launches, but in the end, what we want is to launch a telescope above the atmosphere. But we start small, and the first test for communication, so that we can understand where the balloon is going. So the stratospheric winds in Australia are really not very predictable. So you think you launch and it's going in one direction, the balloon, but suddenly it changes. And you don't want students to chase a balloon in the middle of Australia.
That's good to know.
It's fun. It's going to be fun. We just need
And the other one is winds are crazy. Like when you track the movement, it's one of the best examples of ground movement. Ground movement. That's exciting.
Bueno,
And you know how to it.
we should collaborate. Yes.
We are going to begin.
yo tengo en español por protocolo, pero
Okay.
bueno, muy buenas tardes a todos. Vamos a comenzar entonces con esta sustentación pública de tesis del programa de maestría en ciencias astronomía. Hoy tenemos al estudiante Paula Jessica González Prieto, quien va a presentar su tesis titulada Precursor Mechanisms of Solar Flares, Validation of the Flare Anticipation Index, FAI, through Soft X-ray Observations. El director de esta tesis es el profesor Santiago Vargas Domínguez y el codirector es el profesor Juan Camilo Huitrago Casas. Hoy tenemos como invitados, como curador de la tesis, al profesor Benjamín Calvo Mozo del Observatorio Astronómico Nacional y a la profesora Alina Donea de la Monash University en Australia. Paula, entonces explico el procedimiento. Primero viene una exposición de máximo 45 minutos en el cual defiende su tesis. Luego de eso pasaremos a las preguntas por parte de los jurados y finalmente a comentarios por parte del director y del codirector. Bien, entonces comenzaremos en este momento. Puedes iniciar tu presentación.
Muchas gracias. Well, I'm turned to English, and good afternoon. Thank you very much for being here. I'm going to present my master thesis. The name is Precursor Mechanisms of Solar Flares, Validation of the Flare Anticipation Index through Soft X-ray Observations. This work was carried out here in the Observatorio Astronómico Nacional de Colombia and was complete at the University of Graz and KU Leuven. Thanks for the Dynason project collaboration. In this presentation, we will talk about physical processes that occur before a solar flare in order to anticipate or look for different signatures that can be a good predictor or for anticipate solar flares. To begin, it's important to remember that the sun is an active star, is a magnetical active star, and in his atmosphere we can find different phenomena.
Me or Alina, did you see the first slide or the second slide? I see the first slide.
Oh, it hasn't changed. Yes.
Oh. Let me.
I see a plot.
¿Será que hay un retraso?
Now you can see the second slide.
Yes.
Yes. Okay.
¿Por qué no cambia retroceder aquí?
The first slide.
Yeah. First slide.
Second.
Second slide.
Third.
Oh.
Yeah. Okay.
Thanks.
Thank you.
Okay. Thank you, Milo. The solar atmosphere is highly and strongly influenced by magnetic fields, and in particular, magnetic reconnection can producing different events like sunspot, active regions, and solar flares. These solar flares are the most intensive events in the solar system. And what is a solar flare? Solar flare are sudden and intense release of magnetic energy in the solar corona, often associated with active regions and magnetic reconnection. These events can last from minutes to hours and can release energy up to 10 to the 38 ergs. The mechanisms that we find here are converts magnetic energy into plasma heating, particle acceleration, and radiation. These events can affect our planet, our different satellites, and also some modern technology on the Earth, and can disrupt radio communications or GPS navigations. For that, it is important to study these big events. For understand how to anticipate or how to predict these events, it is important to study the phases of the solar flare. There are three main stages. The first is the preferred phase, when the coronal heating up slowly. The second is the impulsive phase, when we found a big amount of release of emission of radiation. And the third phase is the decay phase. If you can see here in the sub-X-ray curve, there is an increase in this curve just before the impulsive phase. For that, for now, in our work, it is important to study this data. Sub-X-rays directly trace the hot coronal plasma, and GOES provides us continuous observation since 1980s, and it gives us the one measure for the full disk integrated emission. From we can derive a temperature and emission measure. These are our parameters that we wanted to evaluate in this work. First, the temperature is the measure of the plasma thermal energy, and one solar flare can typically have measures from 5 to 40 million of Kelvin, and the emission measure is the amount of emitting plasma that we find in the sun at one time. We often see in different observations that before the impulsive phase, we find an increase in the emission measure and temperature, and in the sub-X-ray data, as we can see here in this plot. Hugh Hodgson based his work on these observations, and he called it a hot onset precursor event, or HOPE. That is this increase in the sub-X-ray data just before the impulsive phase. If we plot temperature versus emission measure at this time, we can see this HOPE like this horizontal branch, when we can see that the amount of the emitting plasma is increasing before the main reconnection. For that, Hugh introduced a new index called Flare Anticipation Index, when he analyzed temperature and emission measure derived from the sub-X-ray data. He analyzed this index through 4 days in 2024, and our motivation is to do a statistical validation with a big, large data set, and try to found good parameters for using this in operational missions, and try to interpret these precursors physically. This is how the flare anticipation index looks. These are the parameters that Hugh used, and these red vertical lines are the trigger or FAI alerts that appear when we will have in a near future a solar flare. The flare anticipation index is a binary threshold-based detection that depends of three parameters. First, the delta emission measure or the threshold of emission measure is greater than one threshold. He used here 0.005. And second, the temperature is between 7 and 14 million Kelvin. And these characteristics persist during 3 minutes, 3 consecutive minutes at least. When these three conditions are present, we will say that there is a FAI alarm or a trigger. And we are detecting significant plasma heating, and we are identifying a pre-flare Tellman buildup, and these signals are these signals of this HOPE or hot onset precursor event. For this work, we use GOES satellite series because we have 45 years of data, continuous data, and we can have this data in real time. So we can use these parameters in real time in order to anticipate and use these parameters for observe better solar flares. We have continuous data since 1975, and we use the X-ray sensor from GOES that measure the emission radiation in two channels, XRS-A and B, from 0.524 and 128 angstroms. The data that we have is the measurements of the full disk of the sun, and these measures are taken with this physical regime that we have optically thin coronal plasma, and the sub-X-ray data comes from thermal emission like Beck-Stallone, recombination processes, and line emissions. One of the limitations of this satellite is that we don't have spatial resolution because we have one measure for the integrate emission from the all active regions on the sun. Well, the data set is, we choose data from 1980 to 2025, 45 years of observations, and the original cadence is 2 to 3 seconds, but we resample this to 1 minute resolution to consistency, and we filter some data because we need a continuous observations in both channels. So we filter days when we have at least one gap of 1 minute. At the end, we analyze 8,000 of days. It is important to do this analysis to subtract the background because we have the full the emission of the full disk. So when we have a quiet sun, we already have sub-X-ray emission. For that, we need to only analyze the emission that comes from solar flares. And we test different methods to subtract the background in order to see if it depends of the method and what is the best to analyze only the emission that comes from soft X-ray data. These are some of the strategies that we use. The local preferred minimum background, the daily median background level, and moving difference implementation in this that we use in this work. We adopted the same method that Hugh used for consistency and for evaluate the same method that he proposed, and also because it's a real-time method to subtract the background. So we compare the flux that we have at one time with the flux a few minutes before for remove this background. We found that this methodology is very sensitive to this method, and with this method we have a consistent work with the FAI framework that Hugh proposed. For calculated temperature and emission measure, we used the package of SumPy called SumKit instruments, and the function that we use is calculate temperature EM. This function received both channels, XRSA and B, and use the radio between these two fluxes and use the different assumptions. First, that we have an isothermal plasma, we have optically thin emission, and coronal abundances. With this, we can derive temperature and emission measure for every minute of the data. This is the pipeline of our work. First, data acquisition, second, background subtraction, next, calculate temperature and emission measure, evaluate the FAI or index or the alerts, and then we match these alerts with the FLAIR dataset in all these 45 years in order to see if every FAI alert are related or is anticipate one solar flare. At the beginning, we download 143 days of data and perform all the algorithms for see if it is working or not, and try to do it with the or test it with the parameters that Hugh used. Then we did a second analysis using 1,000 days to test statistical significance and to see what happened with different classes of the flares. And then when the code was complete, we scaled this dataset to 45 years to did the complete statistics. When we did all these different tests, we found different problems or false positives, false negatives alerts in this process because we have or GOES provides full disk integrate emission, and we can find different or many solar flares at the same time on the solar disk. And these overlapping flares can give us ambiguous flare alert associations or conditions. And for analyze what happened in an ideal context, we remove the overlapping events if we have two solar flares very close, less than 20 minutes separations. We also exclude early start flares when we don't have sufficient data, pre-flare data. because when we when we filter some days that have gaps, some of the flares that are at the beginning of one day don't have enough data before, because we don't have the day the previous day. And we also filter some of the FAI alert if we have these FAI alerts after the peak of a flare or very close of one flare, and remove also the FAIs at the end of the day, because maybe we can associate this to the another day for the gaps that we can found. For that, we have now 4 criteria for the flare anticipation index. First, the temperature range. Second, positive delta EM. Third, the minimum duration. And fourth, a preferred temporal window, because we associate one of the FAI alerts to one solar flare if this FAI alert is or was close to the flare. When we test the parameters that Hugh used, we see that we have a lot of false alarms. We have different solar flares, or many solar flares that were not anticipated. And for that, we wanted to analyze different configuration of parameters. For that, we did a systematic parameter sweep to evaluate the detection and false alarms. To see which are the better parameters, we did this heat map testing different values of the EM threshold and different values of temperature. Here we have the false negatives, and these colors means the percentage of the false negatives that we have testing these different parameters. In these 2 plots, we have both false negatives and false positives. False negatives means the solar flares that were not anticipated, and the false positives are the FAI alerts that are not associating to one solar flare. So we see if we decrease the false negatives, we increase the false positives. For that, we analyze what is important for us. If anticipate every solar flare, or anticipate few solar flares, but have a few false alarms. And for understand how it changed the detection rates and the false alarms, we need also to see how the temperature and the emission measure change if we have different classes of solar flares, and understand this detection behavior for identify the optimal configuration. So we test it in 45 years, initially with 16,000 days, when we filter the days that have gaps. We have 8,000 of full days, and we analyze 48,000 of flares. We can see the distribution of the solar flares here. We have a lot of C-class flares and few X-class flares, such as 200 of X-class flares. So first, we try to see if we have a correlation between the flux and the emission measure, and the flux and temperature. This plot is at the peak time of the flare, and we see a positive correlation with the soft X-ray data and emission measure. And we can see also a correlation with temperature, but is more dispersed every point. This is the correlation at the start time of the flares, and we can see also the correlations. As we cannot see very well the correlation, we did another graphic with temperature and emission measure at the start time, peak time, at the end time, to see how it changed for every class of the flares. With this graphic, we in our set the parameters, but emission measure change a lot. And for that, we test different parameters or different values of the delta emission measure. This is one of the performance of the testing different values. Here we choose the temperature between 8 to 35 million Kelvin. And in the X-edge, we have delta EM explored from 0.001 to 0.5 with increments of 0.001. So we tested 500 values of this threshold of EM. And we plot the detection percentage per every class of the flare. And this is the percentage of detection if we have at least one value, one FAI alert before the peak of the flare. But here we use the parameter of 4 minutes of duration. So remember that if we have, for example, here with 0.001, 95% of detection, it can be one FAI alert before the peak of the flare. But one FAI alert means 4 FAI alerts, 4 consecutive FAI alerts. And we can see if we increase the delta emission measure, we decrease the detection rate. And here is the same plot, but the detection before the start of the flare. So we have a lot of FAI detections between the start and the peak of the flare in the rise stage of the flare. And we also analyze what happened with the false alarms. And we see that if we use like 0.015 of the delta emission measure, the false alarm decreased a lot. And we tested all these parameters varying the duration. So we use 2 minutes, 3 minutes, 4 and 5 minutes in order to see which are the best set of parameters for our study. Every plot of this, 2, 3, 4, and 5 minutes are 500 of values of EM. For that, we choose a temperature range between 8 to 35 million Kelvin, and we test the emission measure threshold in 4 values: 0.001, 0.015, 0.07, and 0.5. In order to see if with these values we can avoid the detection of different classes of the flare. If we choose a low delta M, we detect a lot of precursors, and we detect weak solar flares. But if we increase the delta M, we select the more stronger events. For our first delta EM 0.001, we have these statistics. These columns are the percentage of the detection rate. For X-class flares, we have a 94% of the detection, is very high. And we have a 27% of false alarms. And we plot the anticipation time relative to the flare start and relative to the flare peak to see if the detections are between the start and the peak or before the start of the flare. And we can see that this method found a lot of fire alerts during the rise time, because it's when the temperature and the emission measure increase a lot. Also, we wanted to plot how many fire alerts we have for every solar flare. For X-class flares, we have more fire alerts before the start and before the peak time of the solar flares. And if the solar flare is weak, like C-class flare, we have less fire alerts. But we can have one fire alert before the peak and before the start of the flare. But remember that one fire alert is two consecutive fire alerts. So 4 minutes, 4 consecutive minutes. So 4 minutes to anticipate. Also, we normalize the anticipation time and to see if we have a lot of anticipation after the start of the flare. So all this data between 0 and 1 are the fire alerts during the rise phase. We have false alerts. So we wanted to see what happened with these false alerts, or what happened with these flares that are not anticipating. And we found that if the rise time of the solar flares are very short, if we have very impulsive flares, it is not possible to, we don't have enough time to analyze or to find these previous signatures, because the plasma heating up very fast. So we don't have time to trace the increase or the increment of temperature and EM. So that is what we think, that we have many false negatives or flares that are not anticipating. If we increase the delta emission measure, we decrease the detection of B and C-class flares and reduce the false alarms. We have here only 11% of false alarms. And the detection rate of X and M-class flares remains high. We have 85% of detection rate of X-class flare and 60% of M-class flares. But the duration, the anticipation time is reduced because we have more restrictive parameters, and we have less time to anticipate solar flares. if we reduce also, if we increase the delta EM to 0.07, we can avoid the detection of the C-class flares, but the detection of the M-class flare reduce a lot. And we increase the false alarm rate. With 0.5, we don't have detection, or we only have detection for X-class flares. So with these values, we prove that the anticipation time behavior depends of the threshold of the emission measure. If you will have a low threshold of emission measure, we have longer lead times. If you have a high threshold, we have shorter lead times. And here we can see the four values at the same time to see how it reduced the detection of every class. So these are the values that we choose that reduce completely one class. If we have a 0.01, we exclude A class, exclude B class, C class, and M class. Also, we test what happens if we avoid the upper limit of temperature. And we found that it's almost the same statistics. So the FAI depends only on the minimum temperature, the delta emission measure, but not on the maximum temperature. And this is the comparison of all the configurations that we test. The first one is the parameters that Hugh used. And we think that the best is the third one with the 0.015 delta emission measure. This is one example that how it looks. This is one X-class flare, and the gray lines are the FAI alerts. The pink red lines, the pink vertical lines are the real or the true FAI alert. That means that the conditions remains 4 minutes, and the red lines are the FAI alerts that are associating to one solar flare. You can see here different gray lines that are not associating to another solar flare because we don't have here another solar flare. And this is one case when we didn't anticipate this solar flare, and it is because the impulsive phase, the rise time of the solar flare is very short, so we don't have enough time. As you can see here, we have 3 grain lines, but we are using here 4 minutes of duration. So it is not, there are not enough time to anticipate it. So we need that the rise time, that flares that have a big rise time. And these are one of the limitations because we have the full disks of X-ray observations. And it is because we can have at the same time on the solar disk different solar flares. And it is difficult to know if one of these FAI alerts is alerting this or this or this solar flare. So for that, we have also false positives and false negatives. Well, we interpret this pre-flare phase as a heating or a thermal evolution before the impulsive phase. So the pre-flare heating is real, observable, and we can use this and see these Hubble onset precursor events before the almost every solar flare. We test this in all this data, 45 years of data in different solar cycles and in the minimum and maximum because we use all the whole 45 years. And we have with these parameters a strong performance for M and X class flares. And we also see that it depends on the threshold of emission measure. This is the best performing configuration with a false alarms rate of 11%, and it natural filter weak events because this methodology is used to anticipate solar flares for different missions to observe these solar flares. So for that, we are not interested in weak events, but only in strong events. FAI alerts occur at different stages. We can find these FAI alerts before the flare onset or before the start time and during the rise phase. And occasionally we can see this near the peak. So it is important to see what is happening or how the solar flare evolve because every flare is different to another. And in order to do nowcasting, we need that a solar flare evolve slowly. We have some limitations because we assume that GOES XRS assumes isothermal plasma, and we have some sensitivity for weak events, and we don't have a spatial resolution. For a future work, we want to combine this work with spectral resolve instruments like RESI or SDO and incorporate multi-wavelength observations and explore machine learning approaches. This work was presented in many conferences, the European Solar Physics Online Seminars, the Parker Heliophysics Scholars 10th Meeting, colloquiums in the University of CRAM in Brazil, the International Astronomical Union Symposium in Medellin, and we submit the proceedings for this symposium, and we have now the manuscript, the paper in preparation for publish these results in the near future. And our parameter was used in the Foxy 5 mission like 2 weeks ago, and they tested these parameters. And Milo told us that these parameters perform better, and the fire alerts appear before solar flares, and is a useful study. I want to say thank you to my director, Professor Santiago, my co-director Milo, also to the Group Solar Astrophysics, and the Observatorio Astronómico Nacional de Colombia, also the Dynasome project that give me the opportunity to go exchange to the University of Graz and KU Leuven and work with Professor Astrid Veronic and Jasmina Magdalenik. That was very useful to finish all this study. And these are the key reference for my work. Also, I thank Hugh Hodson that give us the methodology and answer a lot of questions that we have had. And thank you very much for your attention.
Bien, muchas gracias, Paula, por tu exposición. Vamos entonces a pasar ahora a las preguntas por parte de los jurados. Primero le doy la palabra a la profesora Alina Donea de la Monash University. So, Dr. Alina, welcome and thank you for accepting this invitation.
Thank you.
Okay, Dr. Alina, now you may ask your questions to Paula.
Yeah, how much time do I have?
No,
No,
as
no,
long as you
no
need,
tantas
as long
preguntas.
as you need, as long
No
as you
tantas, no.
Well, first I would like to congratulate Paula for the presentation and the results. They seem to be really good, and the effort, the statistical effort that she put into this work to try to validate how many years, 45 years of observations. This is amazing. And I was impressed that she actually recovered the data from GOES from 1975, right? And just to make this data, the continuous data to bring everything into this statistics is very impressive. I have a few questions just to go straight to physics. The first thing here is to imagine the practicability of this application for pre-flare detection. And if you want to show slide 50, I think that's my first, yeah. Yeah, so you have this table here with the all parametric configuration here, and I can see all the statistics here. So the 4-minute oscillation, and you did mention something about the impulsive flares being hard to assess because they are so quick and they last too short, so the heating mechanism is so short.
Yes.
How is this seen in this table? Where are the impulsive, I mean, if I am to catch all these percentages, the impulsive flares, short impulsive flares, where are they here?
We think that the impulsive flares are not we don't have detection of these impulsive flares. For that, for example, yes, for example, we have here for the best parameters 0.015, we have a detection rate of 85% of X-class flares. So we think that the 15% of flares that are not anticipating are they or are close to another flare or are impulsive flares. And for that, they are not anticipating.
All right. And there was another question that I noted here. Page 43, slide 43. Yes, that's one. So you present here the optimal configuration of this, and I'm looking at the confusion matrix here, and I see that 80, the number is it 88% in the confusion matrix. So
yes,
what's the meaning of that? You know, the green top left.
the precision.
I would like the precision in detecting using the FAI alert, right?
Yes, this index.
Okay.
This is the precision of the index with this configuration.
Yeah. All right. And I'm seeing in your performance report here, you have a percent of 85.7. 0.7 it's a very strong decimal here. Do you or is it relevant to introduce errors here, plus minus errors in this statistical analysis? Or do we go precisely for 85.7 decimal? I know that that's a numerical thing, but what do you think would be the errors here?
Yes, it is because we use a real data set. So we have a real number of solar flares, and we say 100% is the 222, I think, X-class flares. So we analyze how many of these total of solar flares are detecting. And this is the percentage that we found. And we didn't introduce errors because we are using real numbers. Like we have this amount of solar flares, how many are detecting and how many no.
Yeah. And the last question here is, all your codes are written in Python? Is it, or what kind of language do you use for
Yes, all is in Python. Mhm.
Python detectors? And if you plan to run this for a pre-flare person, how quickly would a classification run if, let's say, you have an input source? I'm trying to see how quickly you can convert these codes into an operational pipeline. How quickly do you run the statistics if you insert in your codes one single event? How fast is the code
Okay. Oh.
to classify it?
Yes, for one single event is very fast. Let me see. If I try to run with all this data in my computer, that is a small computer, with the whole data, with one configuration of parameters, with the whole data, it lasts like 1 hour, more or less. But with the whole data, 48,000 of flares, but we have already the temperature and emission measure calculated, yeah. Because first, what we did first was download the data daily, and with this daily data, I calculate temperature and emission measure. Then when I have all this data, I did the filtering, and then I matched with the solar flares. And it lasts 1 hour with one configuration. If I test with 500 configurations in a cluster in KU Leuven, it lasts for like 2 hours, I think, but in a cluster. But if you use it in real time, it is very fast because I don't know how they use it in Foxy mission. Maybe Milo can help us with that. But they use it in real time. So they have in real time the lines and how the flux works. The GOES data we can download in real time with 3 minutes of difference, I think, or 5 minutes, because we don't have, or I don't have immediately acquisition. But maybe in Foxy they have the data at the same time. I don't know.
Yeah, okay, thank you, thank you. I'm happy with your answers. Thank you.
Thank you, Elena.
Thank you very much, Dr. Alina. Ahora vamos a pasar entonces a las preguntas por parte del segundo jurado, el profesor Benjamín Canoso del Observatorio Astronómico Nacional.
Gracias. I also want to congratulate you for your good work.
Gracias, profe.
I see that you have. Do you have reconstructed this hope?
Events.
Yeah, which you reported in page 21 of your thesis.
21 or no?
Yeah, you reported.
In Latin. Okay. Yeah. Maybe is your no. Yeah.
For instance, you
Yeah,
have
here.
mentioned.
This the background. Yeah.
Yes. Yeah. Well, my question is this behavior, as long as I perceive, motivates finding this flare anticipation effects as you did it. My question is, has Benz reported also an increase in the pre-flare behavior of flares using extreme ultraviolet signals? Do you think is it possible also to combine X-ray information with extreme ultraviolet? Because they are also available from other sources.
Yes, we wanted to analyze at least one solar flare with UV data, but we don't have enough time in KU Leuven. But the thing is that we don't have data in real time of EUV data, and we don't have enough data.
Yeah,
We don't
yeah,
have
yeah.
45
So
years
not
of data.
45
Yeah,
years.
but we wanted to analyze how it also work. I did. I wanted to s- to to plot these images here, but I don't have enough time to see how evolve the temperature emission measure and the image of the EUV data. For now, I only have this, but we were thinking about that, and in the future, I think we will do.
Is if you use this data, maybe I don't know, is there exists or not some correlation?
Yes.
Signals.
Yes. Yes.
This could increase your prediction.
Yes. Yes. Yes.
Okay. Have you explored some of the physics involved in the prediction of Earth? I mean, what happens when you see a single or multiple combinations? In or restructuring not as a single one, but in multiple flux tubes, for instance.
We think that this increment in soft X-ray data, it is because we have a lot of recombinations and like small reconnections before the main reconnection. That is because the impulsive phase, and we think that happened. For that is that a Foxy mission tried to observe how solar flare evolve and have new data, because until now we have the data of the whole disk, and we can see very well how the flare evolve. But we think that this increment is because something happened there. The amount of emitting plasma increment, and we have a different something is happening when you have a lot of heated plasma in one part in the active regions.
Bueno, pero quiero hacerle una pregunta en español.
Sí, señor. Adelante.
Me disculpa, Lina. ¿Qué futuro ves tú, digamos, con el ánimo de perfeccionar este trabajo?
Ujú.
Porque veo que estás en una etapa donde siguen como que odian una ventana.
Sí,
¿Cuál sería esa perspectiva?
en español. Pues es lo que pues estamos pensando y planeando para el doctorado. Y es, bueno, ya que tenemos toda la estadística y vemos cómo se comporta, porque pues primero queríamos ver estadísticamente cómo se comporta y cuáles son los errores. Entonces, cuando yo encontraba, por ejemplo, esos falsos positivos, esos falsos negativos, ¿qué es lo que está pasando? Entonces, ver cuáles son los casos. Entonces, ya teniendo esos casos como claros, ya ahí ya podemos aplicar Machine Learning, que nos diga qué otras firmas observables ve que nosotros de pronto no vemos porque es un dataset muy grande. Eso uno. Otro, pues hacerle la combinación con algunos otros parámetros, ya lo que decía el profe con otras bandas y otros instrumentos, porque aquí estamos usando, por ejemplo, que el disco solar completo es una isoterma, pero cada fulguración es multitérmico, tiene diferentes estados. Entonces, a mí pues, me gustaría poder ver cuáles son las diferentes temperaturas y cómo está evolucionando en esa parte. Pero son los datos que le cuento que no alcanzamos porque se demoraba mucho en descargarme y pues estaba usando el clúster para correr estas 500 que sí duraba pues bastante, al inicio bastante, ya después cuando aprendí cómo hacer con los diferentes núcleos y tal, fue muy rápido. Pero al inicio mientras uno no alcanzamos a descargar porque la profe Yasmina tenía esa idea de coger una imagen y coger así fuera una fulguración y analizar los parámetros que yo tengo, por ejemplo, las líneas que me aparecían ahí, entonces cuántas tengo yo y qué está pasando en la imagen que estoy viendo yo ahí. Eso era lo que queríamos hacer, pero solo alcanzamos a hacer el video como viendo cómo cambia la temperatura, cambia la media de emisión, cambian los rayos X blandos y las líneas aparecen.
Sí.
Entonces, pues esa ya sería la idea para el doctorado, porque tengo todos los datos, o sea, tengo todas las temperaturas, me tocó comprar un disco para sacar del clúster y traerme, porque
Por tu perspectiva y muchos sectores.
Gracias, profe. Muchas gracias, profe.
Muchas gracias, profesor Benjamín. Ahora entonces, Paula, pasamos a comentarios por parte primero del director y luego del director. Entonces, director, Santiago Vargas, nuestras preguntas.
Bueno, Paula, I probably will switch from English to Spanish. So first, I would like to congratulate Paula for this excellent work. I mean, it's amazing, all the amount of work, of data, of commitment that you have had since you started like a few years ago in the group of solar astrophysics. I mean, it's amazing how you have evolved through the years, and now you have experienced a lot of interesting motivation and also inspiration for carry on along this academic path. So thank you very much. I will also thank Professor Alina, Professor Benjamin for spending time reviewing this work, and it's obviously very interesting to have their opinions and their inputs about this work. Ahora me muevo a español para mencionar hechos interesantes en tu trabajo a lo largo de estos años, porque comenzaste un poco sin tener mucha idea de en qué querías trabajar en tu parte de pregrado, en tu trabajo de pregrado, pero rápidamente tuviste una entrega total hacia el trabajo, hacia el análisis, hacia aprender todo el tiempo, y bueno, lograste un trabajo de pregrado que fue uno de los mejores de la facultad, del departamento de física, y luego pues ya tenías una transición casi que inmediata al trabajo de maestría. Por eso creo que es una de esos estudiantes que todo director quisiera tener, porque prácticamente ya seguiste un camino muy potente. Aprovechaste también la colaboración Dynason, y de hecho en estos 2 años que llevas en la maestría has estado más tiempo afuera que aquí, lo cual creo que es un triunfo para el observatorio. Ojalá todos nuestros estudiantes tuvieran esa posibilidad de interactuar con tantas personas, con tantos investigadores, de tener la experiencia en centros líderes en investigación, y creo que tú aprovechaste eso de la mejor manera, ¿no? Contactaste personas, te empapaste, entraste también en ese ambiente social y de colaboración y de amistad, yo creo que es importante. En cuanto al análisis de datos, como lo mencionaba la profe Alina, trabajar con una base de datos tan amplia es muy complejo, es muy complicado, y de hecho,
Sí.
pues la evidencia es que Hugh Hudson, cuando saca este índice, pues trabaja con unos poquísimos datos y de hecho saca una publicación, y eso ya es algo que llama la atención, pero el salto que tú diste fue abismal, o sea, fue astronómico.
Sí.
De pasar de unos pocos datos allá, 50 años de datos, me parece que era lanzarse ya al agua y a la piscina con todo lo que eso implicaba. Pero creo que enfrentaste problemas muy serios a la hora de analizar los datos, porque no teníamos un servidor, no teníamos capacidad de cómputo, y eso pues se pudo solucionar por el camino, y creo que esa experiencia, que probablemente sea reconocida como habilidades blandas, es supremamente importante para formar investigadores en cualquier área de conocimiento. Quiero agradecer también a Milo. Si no hubiera sido por Milo, pues este trabajo no hubiera llegado a buen término. Milo nos ha acompañado a lo largo de 5 años, tal vez.
Sí, sí, sí.
Y saber que esto que tú hiciste pudo aplicarse ya en Foxy 5, pues me parece que es ya dar un respaldo muy fuerte a un trabajo de maestría que no se queda en los anaqueles, sino que de verdad se va a utilizar y va a ser determinante de aquí en el futuro para misiones espaciales y para muchos otros trabajos de alto nivel. Así que nada, felicitarte a ti, felicitar a la familia también por el apoyo que te ha dado en estos últimos años, y bueno, esperar que en el doctorado podamos seguir avanzando en cosas tan interesantes como, sin duda, Machine Learning, utilizar algoritmos de inteligencia artificial, que como, no sé si lo mencionaste, pero en algún momento sí escuché que lo mencionaste, no lo aplicamos directamente en este trabajo porque uno tiene que primero hacer la primaria y luego el bachillerato. Tiene que primero empaparse de toda la estadística normal con los datos, empaparse de los datos, saber exactamente qué se está haciendo, y luego sí dar el salto a utilizar técnicas que probablemente nos lleven a las mismas conclusiones y más, pero ya habiendo hecho este primer paso. Así que nada, felicitaciones, y también, no sé si pusiste todos los trabajos, porque, claro, muchos de estos trabajos también los has presentado. No sé si en Spectra tienes trabajo
Pero del pregrado.
de pregrado. Perfecto. Sí, se pasa el tiempo muy rápido.
Sí, se pasa rápido.
La maestría.
Sí.
Sí, sí,
La
sí.
felicitación.
Gracias, profe. Muchas gracias, profe.
Muchas gracias, profesor Santiago Vargas. Ahora le doy la palabra al director de la tesis, profesor Juan Camilo Ramos.
Okay, back to English. So the first thing I want to say, everybody's congratulating Paula, and I only want to join that congratulation. It's been a pleasure to work with Paula. What I want to say to start is that Paula not only achieved the original goals that we set for the thesis, Paula went way beyond what we set initially. We wanted to run a statistic assessment of what you hypothesized for the very early stage of solar flares, but Paula got really ambitious, and she didn't want to use just like a couple of flares. She wanted to use the whole data set of those. That I'm gonna echo Alina. It's a very impressive achievement. It's not easy, and yes, as Santiago said, we don't have the computation capabilities at the observatory. Regardless of that, Paula found a way to find a cluster, learn how to use it. She asked for support every time she had a question. She asked us, and not only us, but the team that was with her by the time she was in Europe. So that's really impressive. That shows the different capabilities, the soft skills that Santiago was talking about. When you don't know something, you go and ask the experts. You save a ton of time, and she learned to do that, and she achieved the results. I also want to highlight the fact that the results that Paula found in her thesis were results that we implemented for the full set of tools that used to fly Foxy 5 successfully. So just not even a couple of weeks ago, the past May 14th, we successfully launched Foxy. And that was because we were using many tools, and within those many tools that we used, we had that flare anticipation index that, in fact, we call it Paula's FAI. We were running 2,000 additional parameters, and we were using Paula's. And I may have like a couple of photos of that setup. You could see Paula's name every so often with a last name. Unfortunately, many of those launch flares that we sell, they were outside of launch window, so we couldn't launch, but we still have definitely those predicted the launch flares. I have comments that later I'd love to discuss with Paula and others about like those very intense and impulsive flares. We got to see some of those, and we saw how Paula's single FAIs came out. So we saw single ones, but because, as Paula explained, the code just called one after 4 consecutive of those single ones. We didn't see that. And those flares usually come from occluded flares at the thing, which tells you a little more about the basics, what you see and what's these very early stages, but we'll plenty of talk in the future. I want to also say that Paula's results are of growth interest. And you could see that every time that Paula went to a different institution within the Dinosaur collaboration, everybody wanted to hear Paula and wanted to see her preliminary results. And not only in those institutions, but Paula showed some of that, showed us some of the other talks that she gave in Brazil remotely. And I have to say, within the Foxy team, and not only Foxy, but the HiC team, that is another sub-bucket, and the Magics team, there was a lot of interest to hear and to learn about Paula's results. And multiple times I was like, Paula, can you join this meeting and show us your results? And just at the very end, when we were preparing for Foxy 5, I asked Paula, can you give me the optimal parameters that you prefer? I want to implement that. Paula have them ready. So results from Paula's thesis not only show the usual results, which is like, a very impressive statistical analysis, but something that has been applied, successfully applied, and is operational already. Also, it's been a little like, Paula has been busy, I've been busy, we all have been busy. But I have to say, that paper that summarizes all these results, it's pretty much done. It's almost ready for submission. So it's more like logistics that we are waiting. But I have reviewed it. I think in a few days, a couple of weeks, we would be at a stage that I feel comfortable submitting that to a peer review journal. So that's coming in addition to these proceedings that Paula telling us about. And with that, I just want to finish by saying for me, it's been a full honor to work with Paula all these years. And I also want to echo Santiago. Paula is one of those students that every single supervisor dreams to work with. And for this last sentence, I'm going to switch to Spanish, and this is more for la familia de Paula. Quiero decirles que se tienen que sentir muy orgullosos de la hija que tienen. Creo que ahí está la mamá. La sacó del estadio. Es una astrofísica muy valiosa y solo le espera un futuro muy brillante con ese tema.
Muchas gracias.
Bien, muchas gracias, profesor Juan Camilo Villago. Ok, entonces con esto terminamos la parte pública de la defensa. Ahora voy a reunir con los jurados, a ver ellos qué deciden acerca de la calificación.
Sí, pero un aplauso para la...
y entonces en un momento los haré pasar de nuevo para darles la calificación completa.
Bueno, profe.
Entonces, a Camilo lo voy a poner en un cuarto separado y ahorita lo vuelvo a hacer ingresar al Meet. ¿Listo?
¿Me salgo de aquí, profe, o...?
Sí, por favor, tú saliste, si quieres, voltea, apaga la cámara. Bien, ya que nos siguen por el canal de YouTube, vamos a terminar la transmisión en este momento y luego colocaremos
I think soon, Alina, everyone is going to be with me from the call while you guys discuss internally.
Tenemos que salir un momentico.
Lo estaba viendo por YouTube, alcancé, estaba viajando a llegar a tu ex.
Te presento a mi mami. Mami ya se aleja una amiga.